All right. Hello, everyone. I hope you're all doing well. So today, what I want to do is I want to talk about one of the problems in the homework that's due on Friday. Homework 5 is due on Friday. Some of the problems in homework 5 involve uh, conductors, finding electric fields in and around conductors. And so I want to talk a little bit about that today, just so that you have everything you need to finish all of those homework problems. We will pick one of them. We'll pick the last one, which is probably the most challenging one, and we'll go through and see how we can tackle that particular problem. One of the other updates I wanted to make is that remember that if you want to participate in this hands-on bonus project, up to 3 additional bonus marks, then you have to email me your project proposal by midnight on Monday. And so if you're unclear about what the hands-on project is, then just go to the course syllabus. It's on Canvas or it's on the course website. And there's a whole page dedicated to that. And so you can read about it there. Okay, so we're going to talk about conductors and electric fields today. And so what I want to remind you of is just Gauss's law, which gave us 2 different ways of calculating the electric flux through a surface, a closed surface. One was by evaluating this integral on the left, and then the other was by finding the charge enclosed by whatever surface we're using, and then dividing that by epsilon naught. And those 2 methods had to give the same result. The problem that we're going to talk about today is going to be one that involves a spherical geometry. And so we talked about evaluating these integrals for a bunch of different geometries. One of them was spherical. And the idea was that the electric field would always be perpendicular to the surface. And so we could get rid of the dot product. We could factor the electric field outside the integral. And what we ended up with was just E times the surface area of our sphere. And so if our sphere has a radius r, the surface area is 4 pi r squared. All right, so we're going to make use of that result. We don't have to recalculate it every single time. We're just going to keep that in the back of our mind. And when it's useful, we'll call upon that result. So here is the problem that I want to talk about. I don't care about the numbers. I'm just going to solve it symbolically eventually. But the idea is that you've got a conductor. It's spherical, but it's a shell. So it's a spherical conductor that has a spherical cavity inside of it. And we place inside the cavity a point charge Q. And the question is to find the charge per unit area that's on the inner surface of the spherical shell and on the outer surface of the spherical shell. And then finally, what's the net charge on the conductor? Okay, and so we're going to come back to this. But for now, what I want to do is I just want to talk about, in general, conductors in equilibrium. So for the problem that we want to solve, what we're going to realize is that there's going to be some charge on the outer surface. And so I'll call that Q outer, and there'll be some charge on the inner surface. I'll call that Q inner. And then there is a point charge that sits right at the center of the cavity. Okay, so let's first work out some general properties of conductors and electric fields. Okay, so conductors and electric fields. So what makes a conductor special is that some of the charge inside a conductor is free to move around. And so you probably already know that. That's why we can wire our houses with copper, because there's electrons in those copper wires that are free to move around. If we apply a potential difference of voltage then we can induce a flow of that mobile charge, and then we can power whatever devices we have around the house or whatever. Okay, so some electrons in a conductor, and so conductors include things like you know, the metals, copper, aluminum, maybe brass, silver, gold, all those sorts of things. So some of these electrons are free to move around inside the body of the conductor. So these are called conduction electrons. And so it's important to note that not all of the electrons in a metal are conduction electrons. So for example, what happens is if you have like a copper atom in a piece of copper, it's got what's called like interior core electrons surrounding that atom. And then it has some electrons like kind of near the outside of the atom. And these ones can detach and they're free to move around. And so those are the conduction electrons. And those are the ones that I'm going to be interested in for this discussion. All right. So if I had like a slab of conductor, let's say, so here's some conductor, maybe it's like some sheet with some thickness, and we could imagine that there are electrons in here and they are kind of roaming around, and they can be, each one of them might be going in some different direction, something like this. Okay, so what we're going to do is we're going to talk about conductors in so-called equilibrium. And what we're going to mean by equilibrium is that such an object would have no net flow of its conduction electrons. And so those electrons in there can be moving around randomly, but if we were to write down the average positions, they wouldn't be changing over time. So they're all moving around randomly in arbitrary directions. But another way to think of it is if I was to count the number of electrons in some area, some volume of this conductor, that number would always be the same. Some would leave that volume, but others would come in and conserve the density of charge in that area. So a conductor is said to be in equilibrium when there is no net flow of charge in any particular direction. That doesn't mean charge is not moving. It just means that it's moving around randomly. So charge can still move around randomly, but in equilibrium, there cannot be any net motion in any single direction. We'll see later in the term that we will consider conductors not in equilibrium. And so there will be a net flow of charge in one direction. We'll call that flow of charge a current, and we'll analyze little circuits that involve these conductors not in equilibrium. The way you make a conductor not be in equilibrium is you provide a voltage difference across that conductor using something like a battery or something like that. Okay, but for now, let's imagine we have conductors, no battery or anything like that. So there could be no net motion of this free charge inside the conductor. And everything we're going to talk about today will be a consequence of this definition of equilibrium. Okay, so the first thing that we'll say is that I'm going to claim that the electric field inside a conductor in equilibrium has to be zero. Okay, and so we'll try to justify that claim. So for a conductor in equilibrium, the electric fields inside the body is zero. Okay, so how can I justify that? Well, let's draw our slab of conductor again. And I'll put in a bunch of electrons. I won't yet draw how they're moving, because what we're going to do is we're going to assume that, let's say this is a conductor and it is in equilibrium. Let's assume that we break this claim. Let's assume that the electric field inside that conductor is not zero, and let's see what happens. Okay, so if E is not zero inside the conductor, and so I'll draw an electric field in a second. So let's say as shown above. Okay, so let's say that there is an electric field. I'll just make some arbitrary electric field here. So I'll draw the electric field as being kind of in this direction. And so there's all these electric field lines acting throughout this conductor. And so we have a bunch of charges in there. Charges interact with the electric field, right? We know the force on a charge is E times Q. And so this time, if we have electrons, the charge Q is little e. It's the charge of an electron is minus 1.6 times 10 to the minus 19 coulombs. So if it's not zero, if the electric field is not zero, it exerts a force of, say, F is equal to minus E times the electric field on the mobile charges or electrons. Well, because these are negative charges, the force on them is in the exact opposite direction of the electric field. And so we're going to have all of these forces acting on these charges. And if the electric field is the same at every position inside this conductor, all the forces will be in the same direction. All of these electrons then will accelerate in the same direction, and they'll all tend to move, in this case, towards, say, the bottom left. Okay, so this force would cause the conduction electrons to all accelerate / move in the same direction. And so if they're all moving in the same direction, then there's a net flow of charge in the same direction, and that breaks our assumption of the conductor being in equilibrium. And so therefore, this conductor cannot be in equilibrium. Okay, and so it must be the case then that if we have our slab of conductor, and if it's in equilibrium, we have a bunch of charges in here, but they're going to move around in random directions, like so. And it must be the case that inside we have E equals 0. And so a couple of your questions in this week's homework might be something like, you have a conducting cylinder. Maybe there's some charge on that cylinder. What's the electric field inside? Well, the answer would just be zero. So you cannot have an electric field inside a conductor if we assume that it's in equilibrium. So a lot of these questions where you're asked, what is the electric field inside the bulk material of a conductor? The answer is going to be zero. Okay, and that's our justification is based on the, let's see, it's based upon the definition of what we mean by equilibrium, no net flow of charge. Okay, so that's the first result. Let's do another one. The second claim is that while the electric field inside the conductor is zero, it might not be zero outside the conductor. And so we can talk about what is the conductor, what's the electric field around the outside surface of our conductor. Okay, so for a conductor in equilibrium, the electric field just outside is perpendicular to the conductor surface. Okay, so that's our second claim, and we're going to try to justify this basically using similar sort of logic as we did for the first claim. And so, okay, so we'll draw our slab of conductor again. And we'll try to do this kind of argument in the same way. We'll try to break the claim that is made here by assuming that there is an electric field just outside the conductor that is not perpendicular to the surface, and we'll see what the consequence of that is. So if there is an electric field outside, outside our conductor that is not perpendicular to the surface. So here, let me draw that before I finish this thought. So we'll imagine that we have an electric field, you know, that makes some kind of arbitrary angle with the surface. Okay, well, if that's the case, what I could do is I could imagine breaking this electric field into components. I'm going to make one component that is perpendicular to the surface and a second component that is parallel to that surface. So if we do that, we'll have like a E perpendicular, and then we'll have a E parallel. Okay, so what? Well, we know we have a bunch of charge inside the conductor that's free to move around. And some of those charges will be sitting very close to the surface. And so we could have like an electron that's sitting here. And if that electron is sitting there, it will experience a force due to the electric field that's sitting right at the surface. And if there is a parallel component, that parallel component will cause the electron to move parallel to the surface. And so now we would have like a flow of these surface electrons that are going in the opposite direction of E parallel. There's also a perpendicular surface, but our electrons cannot leave the bulk of the metal unless that perpendicular electric field is very, very strong. And so there's, you know, I'm sure you've seen when you have like conductors with very high voltages next to each other, you can pull electrons off the other, like you can get arcing, these little sparks or like lightning bolts that go from one to another. So that you're actually pulling electrons out of a conductor across a gap to a second conductor. And so in that case, you need very strong electric fields to do that. If the electric field is not that strong to cause that kind of breakdown, the electron won't be pulled out of the surface by this perpendicular, E perpendicular. Okay, so the result is that we get some force, F, on these surface charges that would tend to cause them to all flow in the same direction. Okay, so if we have an electric field outside the conductor that is not perpendicular to the surface, it causes electrons near the surface to flow in the opposite direction of E parallel, and therefore the conductor is not in equilibrium. So we require E parallel equal to 0 for conductors in equilibrium. Okay. So let's think about one more. Well, okay, let's do this. Let's do example. Let's consider a conductor in equilibrium placed in and let's say in a uniform electric field. In fact, what you'll do next week in the lab is you're actually going to map out electric fields for different configurations of electrodes or conductors. So you'll have a carbon piece of paper. Carbon is a conductor. You'll apply some voltage on that paper, and so you'll establish some electric field. And then there's silver paint with different patterns of conductors drawn on top of the carbon paper. And you're going to look and you're going to try to map out what that electric field looks like. And so here's an example of doing that kind of thing. So let's imagine that this is our spherical conductor, and E is equal to 0 inside that conductor. We know that. Then we're going to place it in a uniform electric field. So we're going to have some electric field lines. I'll draw some electric field lines that are far away from our conductor first. So here are some electric field lines. And then I'll start to draw some that are closer to our conductor. And what we have to do is we have to preserve this requirement that the electric field lines near the surface have to intersect at a 90-degree angle. And so what you end up doing is you end up getting a distortion of this electric field. So it'll look uniform far away from the conductor, but close to it, we have these distortions that require the electric field to intersect the surface at a 90-degree angle. And so we get something like this. So these are all our 90-degree angles. And, oh, so that one's, I can draw a straighter line than that, I think. Oh. Okay, and so it comes in, and then I'll have to hit it at 90 degrees. Anyway, something like that. Okay, good. So I want to do one more property of conductors and electric fields. And so this will be property number 3. And the third claim is that, you know, you can have a conductor and it could be neutral, right? So there could be just as much positive charge in the nuclei of the atoms as there are negative charge due to the electrons. And you could have a conductor that is electrically neutral, but still has mobile charge that can move around, mobile electrons that moves around inside. But you could also have a conductor that has some excess charge. You take some of these mobile electrons, you take them out of the conductor, and so now you have more positive charge than negative, and so you have a positively charged conductor. Or you take electrons and you add some extra on there, and so now it's charged negative. The claim is that all excess charge on a conductor resides at the conductor's surface. Okay, so there's a couple of ways to think of it. Let's think about this in two ways. There's kind of a simple way that builds a bit of intuition, and then there's kind of the more mathematical way using Gauss's law, and we could think about both of them. So let's start with the simple intuitive logic. So if we place excess charge on a conductor, okay, so we're going to think about like a spherical conductor with a cavity when we think about this problem number 8 on the current homework. And so let's think about that example. So there's our spherical conductor that has a spherical cavity in the center, and then maybe we can place a bunch of extra positive charge here. And so we place a bunch of positive charge, and maybe like we take a glass rod, we rub it with some felt or something like that, we charge the glass rod, and then we touch it to our conductor, and we can place a bunch of extra charge in some local region on that conductor like we've drawn here. So what happens is, for the conductor, that charge is free to move around, but if we start with it all clustered locally, there's Coulomb repulsion between all the like charges, and that tends to cause them to move away from one another, and so they migrate to the surfaces so that they can maximize the average distance between all of the like charges. Okay, and so this is a non-equilibrium situation, because what will happen is these charges will repel one another, and so they'll tend to move away from each other. And now we have this flow of charge for a moment, and so this is non-equilibrium. Okay, so if we place excess charge on a conductor, those charges repel one another and migrate to the surfaces. And so in this case, because our conductor has a cavity, there are inner and outer surfaces. And this migration is due to the Coulomb repulsion between like charges. Okay, so let's draw what would happen. Sorry, So if we place that positive charge in one local region and we wait just a brief moment, that charge will redistribute itself. And once that redistribution is done, what you'll end up with is charges have maximized the distance between one another by sitting on these surfaces. Now, of course, I'm drawing a 2D picture, but this is a spherical ball with a spherical cavity, and so there's charges spread out over that entire surface area of those inner and outer walls. And so this is now an equilibrium situation. Okay, so with all excess charge on the inner and outer surfaces. Okay. So what we want to do then is, well, okay, let's do another way of thinking about this. So another, oh, what happened? My screen share died. That's not good. All right, so another argument using Gauss's law. All right, so this time I'll take a solid conductor with some excess charge. Do you guys have a question? Do you have a question? Yeah. Okay. All right, so what we're going to do is we're going to imagine that we have a charged conductor. Let's assume that the charge doesn't have to be at the surface. So we just imagine that we have some charge kind of throughout this entire volume of this conductor. And then what we're going to do is we're going to take a Gaussian surface and we're just going to evaluate Gauss's law. Okay, now the one thing we need to remember is that inside a conductor, the electric field is zero. So we're assuming that we have a conductor in equilibrium, there's zero electric field inside, but for the moment, let's imagine that we don't have to have the charge sitting at the surface, we could have it sitting inside the bulk of this conducting object. Okay, and so we pick a Gaussian surface, we'll make it spherical, and so this is a spherical Gaussian surface. Okay, Gauss's law says that E dot dA is Q enclosed over epsilon naught, but we're assuming that E is equal to 0 for our conductor. If E equals 0, that means that the integral is going to be 0, right? If I integrate 0, it's like adding up a bunch of zeros. 0 plus 0 plus 0 plus 0 is just 0. And if the left-hand side of our equation is 0, then the right-hand side has to be 0 as well. And that means Q enclosed must be equal to 0. So if E is equal to 0, then this integral is equal to 0, and we require Q enclosed equal to 0. Therefore, a conductor in equilibrium must have all excess charge at the surface. Right? Because what I could do is I could say, well, look, Q enclosed has to be 0, so maybe I'll just take all those positive charges and I'll just move them just outside the blue dashed line. Then Q enclosed is 0. That's fine. But then what I could do is I could say, well, I'm going to pick a different Gaussian surface. It's still going to be inside the conductor, but I'm going to make it arbitrarily close to that surface. E is still going to be 0 everywhere. And so the integral is still 0, Q enclosed is still 0. And so the only possibility is all that charge is just sitting right at the surface, arbitrarily close to that surface. Okay. So those are the three properties that I wanted to cover for conductors in equilibrium. Now you have everything you need to do the current assignment. And what we're going to do is we'll take a closer look at that last problem, which is the most challenging one. Okay, let's just go back and let's just read the problem here. In fact, maybe what I'll do is I'll just copy this. So can I copy this? Let's see. Hopefully that worked. We'll see. I don't know. Yeah, there it is. Good. So what the problem says is that there's a point charge in the center of a spherical shell. And what we need to do is we need to find the charge density on the inner surface and the outer surface. And then the part 3 is what's the net charge on the conductor. All right, so I can draw that again. So here is our spherical shell. Let's put in some stuff that we know must be true. We know that if this conductor is in equilibrium, the electric field is 0 inside the conductor. Okay, the other thing we were told is that there's a point charge here at the center Q. And in fact, we were told one other bit of information. We were told the electric field is radially outwards and has a certain magnitude right at the surface of the conductor. And so we could draw that as well. So we told the electric field outside is radially outwards and it has, you know, some value, E, I don't care what the value is, some number. Okay, before we tackle the problem, let's just recognize that one of our other requirements is satisfied, and that is that the electric field lines are perpendicular to the conductor surfaces. So that radial electric field is always perpendicular to our spherical surface. All right, fair enough. That's everything that we know so far. So let's find the charge density at the inner surface. Okay, let's see inner surface. So this is part 1 of the problem. Okay, so what we're going to do is we're going to use Gauss's law, and we're going to place a spherical Gaussian surface so that it's just outside that inner surface. Okay, so what we're imagining is that we have some Q inner sitting on this inside surface, and we have some Q outer on this outside surface, and we want to find those values. Okay, so we're going to place a Gaussian surface just outside, so just, let's say, just around the inner wall of our shell. Okay, and so maybe I'll use purple for that. And so here is our Gaussian surface, and we'll call this Gaussian surface 1. Okay, well, Gauss's law requires that E dot dA is equal to Q enclosed. What's the electric field at the Gaussian surface? It's inside our conducting material. So what does the electric field have to be? 0, right? So you could see our purple dashed line is inside our conducting shell, and right beside it, we wrote down that E is equal to 0 inside the conductor. And so E equals 0 everywhere on the surface of our purple Gaussian surface number 1. So E equals 0 because our surface is inside the conductor. Okay, so therefore, this integral is equal to 0 because E is equal to 0. Okay, so Q enclosed. If we look at this picture, what charge is inside that purple dashed line? Someone shout out something. What's inside the purple dashed line in terms of charge? Q and what? Q and Q inner, right? So we have the point charge in the center of the cavity, then there's nothing, then we have that inside surface, and we imagine the possibility that there could be some charge on that inside surface. We called it Q inner. So Q enclosed must be equal to Q plus Q inner. And all right, so we're just gonna combine those results. So Gauss's law requires that the integral, which is 0, be equal to Q enclosed over epsilon naught, which is Q plus Q inner, divided by a constant. I don't care about the constant. I could just multiply through, and we would find, therefore, the only possibility is that Q inner is equal to minus Q. Because we require that Q enclosed is 0, and so those two must add up to be 0. All right, the actual question was, what is the charge density? And so it's the charge per unit area. And so that's going to be Q inner divided by the area of the inside wall, A inner. And so I think in my first picture, I said we were going to make the inner radius A and we'll make the outer radius B. Our inner surface is spherical, and the area of a spherical surface is pi r squared. And so this is going to be Q inner is minus Q. The area is 4 pi times the square of the radius, which we used A. And so that's the inner charge density. Okay. Let's see. Let's now do part 2. And we're going to find the charge density at the outer surface. Okay. We're again going to use Gauss's law. This time, we're going to place a second Gaussian surface, and it's going to be just outside the outer surface. So let's place a second Gaussian surface. We'll call it surface 2, just outside the spherical shell. Okay. So it's going to look like this. Like so. This is Gaussian surface number 2. Before we leave this picture, notice that this time the electric field's not 0. The electric field is E. The problem gave us some number for that electric field. So we know the strength of the electric field. So what we require then is that this integral of E dot dA, let's say for surface number 2, has to be Q enclosed over epsilon naught. And then over here, we could say this was for surface 1, let's say. Okay. So what we're going to do is we're going to make use of the results that we've worked out a couple of classes ago. We know that we have a non-zero electric field, and we know that it's spherically symmetric, and we have a spherical surface. And so we know from a couple classes ago that this is going to evaluate to E times the surface area of the sphere. And so it's 4 pi r squared. In this case, the radius is B for the outside of our shell. All right, and Q enclosed. What do we have to include in Q enclosed this time? What are they? Yeah, there's Q in the center. What else? Q inner and Q outer. So now there are 3 contributions. So Q enclosed is the point charge in the middle, plus whatever charge is on the inner surface, plus whatever charge is on the outer surface. But we already know that Q inner is minus Q. And so this is minus Q, and those two will cancel. So the only remaining charge that hasn't canceled out is Q outer. And so therefore we say that Q outer, we just have to multiply by the constant epsilon naught, is epsilon naught times E times 4 pi E squared. That's Q outer. We know E, it was given. We know the radius B, it was given. So we could just calculate Q outer. If we wanted sigma outer, the charge density, we would say it's going to be Q outer divided by the area of that surface, 4 pi B squared. And if we do that, we're just going to get epsilon naught times E. And so that's the charge density at the outer surface. Finally, part 3 was to find the total charge on the shell. And that's easy. We've done all the hard work already. So the net charge on our conductor is Q inner plus Q outer. So we know that has to be the net charge because we proved already that any excess charge on our conductor is going to sit on the surfaces. So if I find the charge on the 2 surfaces, there can be no other excess charge anywhere else in this conductor as long as it's in equilibrium. Q inner, we already found, was minus Q, whatever the point charge is, plus this Q outer, which would be epsilon naught. E is known, 4 pi B squared is all known. And so that's the net charge on our conductor. Okay, good. So with that, then you should be able to do all of the current homework. You know, we just did the hardest problem, but you could apply these kinds of techniques if you have other problems involving conductors and electric fields. Thank you very much. What we'll do on Friday is we'll pick up where we left off, talking about the potential energy. We're going to try to define the potential energy of a point charge and the potential energy between pairs of point charges. All right. Thank you very much. See you in a couple of days. Yeah, see you.